This is a video for AQA Further Pure Mathematics. This is Complex Numbers section 3.1, where we're considering Cartesian to modulus argument form of complex numbers. We've already met the idea of a Cartesian plane to represent complex numbers, i.e. the Argand diagram, where we're using xy to represent the complex number or a vector from the origin to the number. Now we can, instead of using the Cartesian coordinates, we can consider what are called the polar coordinates r and theta. These are calculated by using trigonometry. R is the distance from the origin, it's always greater than 0, and theta is the direction from the positive x-axis. Measured positively, the direction would be anti-clockwise. R is known as the modulus, which is often written as mod z, or using two lines around the z. So the modulus of z is the distance from O, and theta is known as the argument, so the angle is the argument. What are called the principal values of the argument are from negative pi round to plus pi. So on the diagram, going round from the positive axis, then negative pi is round to the negative real axis, and positive pi coming round to the negative real axis in that direction. So notice we've got from negative pi, less than theta, and less than or equal to pi. So pi obviously here in radians. Well, I've said we can convert from the Cartesian form to the modulus and argument form using trigonometry. So you can see here the diagram showing the Cartesian coordinate xy and the polar coordinates r and theta. And we can see then that clearly the modulus of z or r by Pythagoras' theorem is just the square root of x squared plus y squared. The modulus is always going to be positive, so when you take the square root, remember that you're going to take the positive value. The angle theta, so the argument there, is given by tan to the minus 1 y over z, so the opposite side divided by the adjacent side. However, because of the way your calculator works, we have to be careful using this to decide whether we need to add or subtract pi from the answer given on your calculator. We'll do some examples in a minute, but the easiest way of deciding that is to sketch a diagram showing the complex number, and then we can decide whether we need to add or subtract pi from the calculated value of theta. Well, to illustrate these ideas then, and particularly looking at the arguments, I'm going to consider these complex numbers, obviously one at a time. So let's start off with z, which equals 2i. Now if you were to do this on a calculator, then your calculator would say, well, just a minute, we can't actually calculate that because tan to the minus 1 of the y value is 2 divided by 0, and of course you're going to get a maths error there. So we can use a rather more sensible value, which is to say, well, look, it's on the positive imaginary axis, so this angle here must be equal to pi by 2. So tan to the minus 1 of 2 over 0 is pi by 2, and therefore the argument of z in this case is equal to pi by 2. If we look at the next one, 3 plus 4i, tan to the minus 1, 4 over 3, so y over x is equal to 0.927. And we can see that that's going to be the correct value. The diagram shows us that we're in the first quadrant, and indeed, therefore, we can say that the argument of z in this particular case is 0.927. When we look at 3 minus 4i, y over x this time is negative 4 over 3, and that gives us negative 0.927. And again, checking that on the diagram, we can see that this is going to be the correct value, negative 0.927. So in this case, the argument of z is negative 0.927. If we look at this one, however, we get a slightly different result, because this time tan to the minus 1 of negative 4 over negative 3 is 0.927. So that's y, tan to the minus 1 of y over x. So what it's actually calculated is this angle here. So what we need to do then is to go from that angle and come round to here, which we can see is the correct position for the complex number that we're considering. So we're going to have to subtract pi from that answer. Therefore, we can say that the argument of z in this case is 0.927 minus pi. Finally, if we look at negative 3 plus 4i, this time tan to the minus 1 of 4 divided by negative 3 gives us a negative value. So it's actually calculated this angle down here, negative 0.927. So this time, to get the correct value for the argument, we're going to have to go in the positive direction and add pi. So that our correct value for the argument this time is negative 0.927 plus pi, so it's 2.214. If we now consider this diagram again, we can convert from rectangular Cartesian form to modulus and argument form by seeing what the relationship is between y and x and r and theta. So from the diagram, little right angled triangle there, we can see that y will be equal to r multiplied by sine theta, being the opposite side of the triangle, and x will be r multiplied by cosine theta. So we know that the complex number z is x plus iy, so we can simply substitute the values r cos theta and r sine theta for x and y. Now this is usually written with the r outside a bracket, so we get that z is equal to r cos theta plus I sine theta, where remember r is the modulus of the complex number and theta is the argument. So this is what we call the modulus and argument, or polar form of a complex number. It's where instead of using the Cartesian coordinates x and y, we're using the polar values r and theta. So we can look at an example of that then, expressing z equals negative 1 plus root 3i in modulus argument form. Well, I would always suggest that the first thing you do for this is to draw a diagram of what it looks like. So there it are, there's at negative 1 root 3. And if we then calculate the value of r, it's obviously clearly 3 plus 1 is r squared, therefore r is equal to 2. So the modulus of the complex number is equal to 2. So you could write down. If we look at the tan to the minus 1 of y over x, it's tan to the minus 1 of root 3 divided by negative 1, and that gives us negative pi by 3. So remember then that what's happened there is that this is the value of the calculated value of the angle tan to the minus 1 root 3 over negative 1. So what we need to do to get the correct value for the argument is to add pi to that. So the angle theta there is pi minus pi over 3, which gives you 2 pi over 3. So we've got the modulus of 2, the argument of 2 pi over 3. And therefore, putting those into our form of the modulus and argument form, you can see that there we've got r is equal to 2, and here we've got cosine theta plus I sine theta. So converting from Cartesian to modulus and argument form of a complex number. Well, that was the end of that video. In the next one we'll look at doing this the other way around, going from the modulus and argument form to Cartesian form of complex numbers.